Everyone, my name is Marcelo Wallau. I'm the forage extension specialist for UF IFAS.
My name is Esteban Rios. I am the forage breeder in the Agronomy Department at UF IFAS.
And we are the Plant Science Research and Education Unit to show you some cowpea experiments that Dr. Rios is conducting.
So here we have a randomized complete block design with 4 different blocks, and the treatment design is a split plot. The whole plot here in this case are 3 different planting dates. Here I'm standing on a planting date that was basically put into the ground at the end of July. Behind Dr. Wallau, we see something that we planted in mid-August. And then the latest planting date, which was planted 3 weeks ago at the beginning of September. The rationale for having the different planting dates is trying to push planting later in the summer and early fall, with the goal of providing high quality forage in the fall semester and even early winter. At the subplot level, we have 5 different cowpea varieties, 3 that are coming from the USDA, iron clay as the control, and then 1 new forage type release that was developed by Texas A&M, and the name of the cultivar is ACE.
So we always think about an experiment and we always say that a randomized complete block design or even a complete randomized design would be the best. And now we're talking about plots and subplots. Why would we choose to go in a subplot, putting subplots here instead of just completely randomized?
Well, in this case we chose a split plot because of it's easier to manage the planting in this case. So if we had this experiment as a complete factorial, for example, where any combination of planting date and cultivar can go anywhere in this area, then the planting becomes a little bit more complicated. So we chose to have a split plot. So here in this case, each one of these strips that basically look like or they are representing the whole plot, they are all planting at the same time. So it's easier to basically come and plant and also collect data. We are going to be collecting data this week, now at this time of flowering. So basically collecting biomass and nutritive value on this sample. But the short answer is basically ease of management, and that is the split plot is an excellent treatment design to accommodate either machinery or as well as data collection.
Yes, and also it helps accommodate for treatments. As we saw in the other plots, the fertilization treatments, you have a large piece of equipment that you need to run through the plots to apply the treatment. So it's much easier to have a set of them continuously that's applied. But that being said, we also have a randomization we have 2 levels of randomization. We have 1 level of randomization within the subplot, which here in this case is the different varieties, and then we have a 2nd level of randomization that is at the plot level. So in the case here, the dates would be randomized, or in the other trial, the nitrogen rates would be randomized.
So yeah, so if you remember the principles of experimental design, we have replication, randomization, and blocking. In this case, we are applying the 3 principles in this experiment. Why do we do replication? Is because we want to increase the precision of our estimates, in this case for biomass production, and we want to reduce the background variation that is created by having heterogeneous experimental units. The second principle, randomization, and as Dr. Wallau said, it's important to randomize in this case that it is a split plot. We randomize at the whole plot level. It means that the planting date can go anywhere within the block. So we avoid bias in that case. And at the subplot level, we randomize the varieties within each one of the whole plots, again, to try to reduce bias and have varieties placed anywhere in this area. And the third principle is blocking. My recommendation is usually is better to have a randomized complete block design than a completely randomized design. And that is because usually when we are going to collect data, we can also increase the background variation or the error. So if you have a randomized complete block design and you collect data by blocks, you are also reducing that noise or that background variation when you are collecting data. So sometimes we think, oh, my area is very homogeneous, I have a good experimental area where I don't need to do a randomized complete block design, but we also forget that we have to collect data, and we also apply other management practices into our experiment. So that's usually why I recommend having a randomized complete block design against a completely randomized design.
Perfect. So one of the things it's interesting to see specifically in this experiment here, but we also saw on the Bermuda grass experiment, is why it's important to randomize the treatments. And for example, we can see that in this end here of the treatment, there is a slope coming from that way. So if we don't have any randomization, we never know if the varieties here on this end of the plots are going to be better because they are genetically superior, or because there is a little more moisture than that end, or because whenever you applied any fertilizer, the fertilizer was washed out towards this end and here happens to grow better. So accounting for those little details makes a lot of difference when you are showcasing your trial or when you were showing your demonstration plots for your farmers.